everyone to this week's HPL seminar. Our speaker today is Ashna Subramanium. So Ashna did her undergraduate here and started working with Dr. Benonig's lab in her undergrad for her 466 research project. She then continued on to a master's in the same lab and then transferred to a PhD in 2021. And so she's under the co-supervision of Benonig and Walter Kurtzhoff. So her research interests are on the effects of footwear design and construction on running performance, perhaps obviously given the title today. So something that she's kind of proud of is that apparently it's been very difficult to take the carbon plate out of Nike Vaporflies, and a lot of research groups weren't able to do this. And so as part of some of her projects, her group was able to actually get the carbon plate out without seriously damaging the shoe. So today, Ashna will be talking to us about the Teeter-Totter Effect, a possible explanation of the performance benefits of advanced footwear technology shoes.
I'm sure most people in this room would be familiar with a marathon running shoe known as the Nike Vaporfly 4%, which came out in the market about 5 years ago. You would have either seen people breaking world records in those shoes, or some of us testing them here at the lab, and must have heard that they are supposed to improve running performance. But the interesting thing is, despite these drastic improvements in running performance, we're not able to understand what in the shoe or how these shoes are really improving the observed running times. And so part of my PhD thesis is responsible for answering some of those questions through a series of projects. And today I am interested in sharing 2 of those projects with you, one of which we recently completed and prepared for a publication, and the second is still a work in progress. So being about a year away from hopefully graduating next year, I would like to share this work in progress and get feedback from the group in ways to improve my work. The Nike Vaporfly 4% shoe. It's a popular shoe specifically because it was shown to reduce the metabolic cost of running on average by about 4%. It is also popular because it features some footwear characteristics that were not seen in conventional running shoes prior to this model. Specifically, the shoe has 2 soles made of the Pebex midsole, which is a new generation of midsole foam, considered superior to TPU or EVA foams that we've seen previously in conventional shoes. So it has 2 parts of that midsole, between which we have a curved carbon fiber plate sandwiched. And a combination of both of these features creates an upward curvature of the forefoot, also known as a toe spring. So the shoe also has a substantial toe spring. And based on the results that the shoe have shown, the record-breaking performances and the innovative design, researchers have been interested in trying to understand what in this shoe and how we are seeing such improved performances. 5 years later, over the years, people in different lab groups have performed different studies to look at biomechanical variables. For example, contact times, peak vertical ground reaction forces, work at the MTT and ankle joint, etc. They've also analyzed physiological variables like running economy while running in the Vaporfly compared to conventional running shoes. And a recent review in the Footwear Science Journal by Patos and co-authors tried to summarize all of these results in order to see if we can explain the performance benefits from a biomechanical point of view. And what they found is that studies are showing conflicting results. So some studies found that certain variables went up in the Vaporfly, certain variables decreased, and some didn't show a difference at all. And so based on this, the authors of the review concluded that we are not able to explain the better performance observed in the Vaporfly shoe based on the current biomechanical understanding. A previously proposed theory of the Teeter-Totter effect by Nig and co-authors in 2020 may be a way to explain the missing piece in the Vaporfly puzzle. Specifically, the authors proposed that the unique design of the Vaporfly shoe creates a class 1 lever design in the shoe, which allows it to act like a teeter-totter. So if we take the carbon fiber plate which has been embedded in the sole and assume that that allows the midsole to act as a rigid piece here, we can speculate that the shoe is rotating about a pivot axis, which is created by the forefoot geometry of that shoe. So from, for example, mid stance here on the left picture to late stance phase, the runner's shoe can pivot about this pivot axis and have the heel lift in late stance phase. And the author suggests that this teeter-totter motion in late stance phase would produce a reaction force at the heel, like in a class 1 lever. And if we have a reaction force at the heel, this could mean increased propulsion in late stance phase. So as part of my thesis work, my first step was to look at some pilot data to see if we can even experimentally test this teeter-totter theory or that increased reaction force in the rear part of the shoe. To do that, a runner performed overground running at the speed of 3.9 meters per second in 2 shoe conditions. Specifically, our test shoe was this bottom picture, which is an Adidas Boost shoe. At the time, we hadn't ordered the Vaporflies, so this was the closest construction to the Vaporfly, with a drastic toe spring and a Boost midsole material, which is also considered the superior foam material. Our control shoe was this flat Stan Smith lifestyle shoe, and it was chosen, even though it's not a running shoe, it was chosen because the construction of this shoe is not expected to allow a teeter-totter movement during late stance phase. And we arbitrarily chose 3 time points, 70, 80, and 90% of stance, to analyze the force distribution in the rear part of the foot to see if we can see increased forces in the test shoe. And what we see here is the position of the force in the anterior, posterior, and medial lateral direction. And the arrows indicate the total force at that time point at a specific location in the 2 conditions. If we take a close look at the 80% and the 90% time points in both the test and the control shoe, we can see that the test shoe, which has a similar construction to the Vaporfly, shows higher forces compared to the flat one. Another interesting observation is that when you go from 70 to 90% of stance phase, the force is actually moving anteriorly in the flat shoe, while it goes posteriorly in the test shoe condition. So what we conclude from the pilot test is that footwear features and modifying them can change the magnitude of the force that occurs in the rear part of the foot, as well as the location of that force relative to a pivot axis, which here was estimated around the MTP joint or this curvature. Another interesting observation we made from the pilot data was that the Boost shoe or similar constructions, which later was confirmed with the Vaporfly as well, show a very distinct backward movement of the anterior posterior center of pressure position in late stance phase. And if we calculate a difference between this time point and this time point, the center of pressure position gives us a delta XAP, showing us the posterior shift in the position. And this brings into question whether this graph could be an initial indicator of the teeter-totter effect in certain shoes that are showing that increased rear foot force. So having modified or affected the force magnitude in the rear part and the distance of it from a pivot axis, we can affect the moment that is generated to lift the heel in late stance phase during running. And this moment that is generated about the pivot axis is a result of 2 moments. The muscle moment, which would be produced by the forces in the muscles crossing the ankle joint, and the teeter-totter moment, which would be produced from the force that the shoe produces onto the runner's heel. If a shoe construction can increase this teeter-totter moment or add that onto the propulsion moment, we would have higher propulsion in that specific shoe condition. And we can speculate that this might result in a lower overall work requirement during push-off. So far, to make all of those speculations, we have a few assumptions that we made, and just to list them and summarize them here on the slide. First, we assume that the propulsion moment in late stance phase is a sum of the muscle moment and the teeter-totter moment. Then we assume that for one given task, for example, at the same speed and on the same surface, we would have the same muscle moment in two different shoe conditions for the same runner. And lastly, we assume that the midsole of the Vaporfly or certain shoe conditions is rigid across the length due to that inserted carbon fiber plate. Based on these assumptions, we can come up with a methodology to quantify the propulsion moment in late stance phase. And one easy way to do that is to take pressure insoles, put them in the shoes, and have the runners run over ground in the shoe conditions that we want to compare. Insoles are a good way to do that because they give us the force in different regions of the foot, and they also give us the location of that force relative to the pivot axis of the shoe. And that allows us to calculate a moment. Specifically, once we collect data in a test shoe, we can divide the insole into two regions, the forefoot and the hind foot, which is highlighted in blue here. When we sum all the forces in the hind foot region, we can get a resultant force known as the force in the hind foot. And we can calculate the distance of that force relative to the pivot axis shown in blue here. This pivot axis can be determined by applying pressure to the point where we expect the pivot axis of the shoe to be visually, and take that location to understand the relative distance of this force. And although pressure insoles are a good way to analyze or quantify the forces in the rear part of the foot, in order to calculate that moment, we do need to remember that it is giving us the total forces from the muscle as well as the teeter-totter produced by the shoe. And we're not able to effectively separate these two to say what comes from the muscle or the teeter-totter. So that propulsion moment is a total sum of that. However, we are able to estimate the teeter-totter moment by quantifying the propulsion moment in two different shoe conditions. So let's say we have a test shoe with a similar construction to the Vaporfly, where we would expect to see a teeter-totter effect. And then we quantify the propulsion moment in a control shoe, which is completely flat and would eliminate the teeter-totter. And based on the assumption that the muscle moment is the same, we can rearrange that equation and subtract the propulsion moment quantified in the control shoe from the test shoe in order to estimate the teeter-totter in the test condition. And based on our pilot results, we can expect to see different propulsion moments based on different shoe conditions, as we saw the force magnitude and location change. But note that this was only pilot results for one subject over 8 trials, and we don't know whether this happens across different participants. That brings me to the purpose of my study. There were 3 purposes to this first study, where first we wanted to estimate the teeter-totter moment while running in the Vaporfly shoe. We then wanted to quantify the change in the anterior-posterior position of the center of pressure in late stance phase in the Vaporfly shoe compared to a flat shoe. And the reason to do that was to see whether the change in the center of pressure position was correlated with the moment generated by the teeter-totter effect. We hypothesized that running in the Vaporfly shoe will produce a teeter-totter moment. We also hypothesized that there will be a greater change in the anterior-posterior position of the center of pressure in the Vaporfly shoe compared to the flat, and that there would be a positive correlation between the teeter-totter moment and the change in position of the center of pressure. To test this, we recruited 15 male recreational runners who ran over ground at a speed of 3.9 meters per second in 2 shoe conditions. Our test shoe was the Nike Vaporfly 4%, also referred to as VP4 here on. And our control shoe was a Nike Air Force One, which is similar to the Stan Smith that we used for our pilot results, where it is flat, and we refer to it as the control condition. We recorded data using X-sensor plantar pressure insoles at a sampling frequency of 150 hertz. And we also collected high-speed video data during those trials using a Sony video camera that could collect at 240 hertz. We were interested in quantifying the teeter-totter moment in the Vaporfly shoe, in quantifying the change in the center of pressure position, and also in the correlation between these 2 variables. Here on the left, you see a picture of our test condition, which is the Vaporfly, seen quite a few times over the last few slides. But the control condition is a new shoe, which is the Air Force One available on the market. It's a flat sole, as you can see, and so we would not expect it to have a teeter-totter effect where it could roll about the pivot axis. The data collected from the insoles was first filtered using a low-pass Butterworth filter with a cutoff frequency of 25 Hertz, and then stance phase was determined using a 40 Newton force threshold. We then cropped the data from 5 to 95% of stance because it's been shown that pressure insole data is quite noisy at low forces, and by cropping it at 5 to 95% of stance, we can get rid of that noise. We then calculated the propulsion moment using the force in the hind foot and the location of that force relative to the pivot axis, also called the moment arm of that force. We did that for both shoe conditions, the test and the control, as participants ran in both in a randomized order. And then by taking a difference between the propulsion moment quantified in the test shoe and the propulsion moment of the control shoe, we estimated the teeter-totter moment in the test condition. Now, from the introduction, you may remember that the teeter-totter effect takes place in late stance phase, once your point of application of the force has moved anterior to the pivot axis of the shoe. In the pilot study, we just took 3 arbitrary time points, 70, 80, and 90% of stance, just to see how that takes place. But for this study, we wanted to specifically quantify what time point is where we can see the hind foot lift off the ground. We want to be sure that the forces that we're measuring are just the reaction force from the teeter-totter and not from a result of the shoe being in contact with the ground. So the video data that we collected helped us quantify that. And here you see an example of a runner performing one trial in the Vaporfly shoe. And shortly after this mid-stance phase, you will start to see the heel lift off the ground. And at some point, the entire hind foot is off the ground, and the slow, having so many frames per second allows us to specifically quantify where in time we see that hind foot come off the ground. By analyzing the data for those 15 participants, 8 trials, and 2 shoe conditions, what we saw is that across conditions and participants, it was quite consistent when the hind foot lifted off the ground. And based on the analysis moving forward, we analyzed everything from when the hind foot lifts off the ground at about 65% of stance till the end of stance, which is 95% for this case. So going back to our first purpose, our purpose was to estimate the teeter-totter moment while running in the Vaporfly shoe, and we hypothesized that the Vaporfly shoe would produce a teeter-totter moment in late stance phase. Here's an example of a propulsion moment graph that we calculated in the way that I described previously. So on the y-axis, you see propulsion moment in Newton meters, and on the x-axis, we have stance phase in percent stance. You see this dotted line representing the 65% of stance phase, which is the time point where the teeter-totter effect should start. And everything past that is showing the curve for the propulsion moment for one subject, one trial, and one shoe as an example. We do expect that past 50%, once the heel starts to lift off the ground, you would start to see or experience a teeter-totter effect. But as I mentioned, we would not be able to separate what part of the force comes from the contact with the ground or the teeter-totter. We only take the time point once we're certain that the hind foot is not touching the ground. So all the graphs that you see for results of the first objective are going to be very similar. We start by taking a look at one subject performing 8 trials in 2 different shoe conditions, the test shoe presented in blue and the control shoe presented in the orange curve. It is an average of 8 trials with the standard deviation of the trials presented with the shaded area. On the y-axis is the propulsion moment that we saw on the previous slide, but on the x-axis, we now zoom into just the window of interest from 65 to 95% of stance. And what we can see clearly for this one subject is that there's larger propulsion moment in the test Vaporfly shoe. That confirms that there's an added moment coming from the Vaporfly shoe, which is shaded in the green area here, which we call the teeter-totter moment. And it can be estimated by taking the difference between these 2 curves, which is shown here in the black curve. So this is the estimated teeter-totter moment for the first subject. over stat space. We did the same thing for all 15 subjects. So on the left graph, you see 15 curves of the propulsion moment in the vaporfly shoe and 15 curves of propulsion moment on the right graph in the control condition. When we average those, here you can see a large spread in the data set, but what you notice is that the propulsion moment is still larger in the vaporfly compared to the control across 15 participants. And when we average those curves, we get the propulsion moment in the vaporfly condition and the propulsion moment in the control condition for all 15 subjects. Here on the right, we then take the integral of the propulsion moment curves over time for each subject in the vaporfly condition and the control. Each individual subject is plotted here in gray dots, and the average of all the subjects is presented in the solid blue and orange dots. So we can see that on average, there is larger propulsion moment in the vaporfly, confirming the teeter-totter moment. For the average of 15 subjects, it can also be calculated by taking the difference between the two curves, and we see the average teeter-totter moment estimated for 15 subjects in the vaporfly shoe here on the right. Now, one thing important to note here is that even though we took a control shoe that is flat and not expected to create teeter-totter motion, we cannot take away the innate anatomy of the foot. So for example, the MTP joint is responsible for propelling the runner forward in late stance phase. And even though we put the runner in a flat shoe, we still would expect some sort of propulsion by rolling about the MTP joint in late stance phase in this shoe. So if anything, this estimated teeter-totter moment on the right would be a conservative estimate. From the first study, we saw that there was a larger propulsion moment in the vaporfly, and that taking the difference of this the propulsion moment in the two conditions, we're able to estimate the teeter-totter moment in the vaporfly shoe. Confirming our first hypothesis that running in the vaporfly shoe will produce a teeter-totter moment. We brought up a point that this posterior movement of the center of pressure observed in our pilot studies may be an indirect indication of the teeter-totter moment. So we wanted to see from our second and third objectives if we're able to quantify the anterior posterior position of center of pressure in late stance phase in the two shoes and determine whether the change in that position is related to the teeter-totter moment. We hypothesized that there would be a larger change in the vaporfly and that the two variables would be related and show a positive correlation. Here on the left graph, you see the center of pressure position and the anterior posterior direction in millimeters. And on the x-axis, we have the same time window from 65 to 95% of stance. The average of all 15 subjects is presented for the vaporfly in the blue curve and the control condition in the orange curve. So what we expect to see from the pilot results was that there would be a posterior shift in the center of pressure, and we're seeing that happen in the vaporfly shoe, where we expect a teeter-totter effect. In the flat shoe, where we do not expect one, we see the center of pressure moving anteriorly till the end of stance. We can quantify how much the center of pressure moves back by calculating a delta XAP variable, which is taken by subtracting the position of the last point in time from the maximum anterior position of the center of pressure. And if we have a larger delta XAP number, would mean that the center of pressure travels further posteriorly. The delta XAP is plotted here on the y-axis in the right curve and is shown for all 15 subjects in the gray dots, with the averages in the blue and orange dots. What we see is that the change in the center of pressure position is significantly lower in the control flat shoe compared to the vaporfly. Now the question is the change in the center of pressure position related to the teeter-totter moment that we estimated? To do that, we calculated delta XAP for all 15 participants, all 8 trials in the vaporfly shoe, giving us 120 delta XAP data points. and calculated the area under the moment, teeter-totter moment curves for the same data points. And we found that the change in the center of pressure anterior-posterior position explains about 59% of the variance in the teeter-totter moment. So we also confirmed the second and third hypothesis, that we would see a greater change in the vaporfly shoe and that the two variables would be related. From the first study, we can conclude that the vaporfly shoe produces a larger propulsion moment and that this propulsion moment is a result of the teeter-totter moment. We also find that the greater change in the anterior-posterior position of the center of pressure in the vaporfly may be a first indication of the teeter-totter effect. So going forward, some of the possibilities are to estimate the teeter-totter moment in a shoe condition of interest, the way we did in this first study, by taking a flat control and subtracting the propulsion moment to get the absolute idea of what teeter-totter moment looks like in that shoe. We have a second possibility to quantify the propulsion moment for different shoe conditions in order to get a relative understanding of the teeter-totter effect. So, for example, a shoe B, if it has a higher propulsion moment than shoe A, we would expect that it is creating a larger teeter-totter effect. However, this is not done yet, and using the second proposed possibility for the future, we wanted to create a second study to answer another question that is often asked when it comes to the vaporfly. Not only have scientists been trying to explain why the vaporfly improves performance, we are also trying to understand what part of the vaporfly is responsible for the performance improvements. And the three distinct features that we discussed earlier are always concluded to be acting in combination for the improvements that we've observed. So papers always say that a combination of the PEBX midsole, the curved carbon fiber plate, and the toe spring are potentially responsible for the observed improvements. But no one has tried to systematically alter one of these features and see how it changes running performance. So the purpose of our second study was to determine the effect of the different features of the vaporfly on the change in the anterior-posterior position of center of pressure. This was a first objective to see if we can affect the change in the center of pressure by modifying the features. And if that were to happen, then to determine the effect of the different features on the propulsion moment while running. We hypothesized that the original construction of the vaporfly, which includes all of the features that we talked about, would produce the largest change in the anterior-posterior position in center of pressure, and that this original vaporfly will produce the largest propulsion moment in late stance phase. The next slide is probably the most exciting part of my PhD work, where I got to work on the vaporfly shoe conditions and modifications that we included in this study. Like Olivia mentioned, I'm very proud that we were able to effectively separate the carbon plate from the vaporfly without ruining the shoe, but we also did a lot more, and let's go over that one at a time. So the first shoe condition in this study was the original vaporfly. It has the PEBX midsole, it has a curved carbon fiber plate sandwiched in that, and it has a substantial toe spring. For the second condition, we cut out the plate that runs across the whole length of the foot and kept all of the other features of the shoe consistent. For the third condition, we were interested in seeing the effect of the midsole material of that PEBX foam. And so we replaced it with an EVA of a similar hardness, but it does not have the same compliance and resilience as the PEBX midsole. In this shoe condition, we still kept the same profile of the carbon plate that was in the original shoe condition. So the only thing that changed was the foam material. And lastly, this clown-looking shoe was the toe wedge condition, where we wanted to eliminate the drastic toe spring in the original vaporfly. And so the foam that was harvested from this EVA condition was used to create this wedge and eliminate that. So in this study, we recruited 18 male recreational runners who performed the same protocol as the previous study, but now in 4 different shoe conditions: the original vaporfly, the no plate, the EVA, and the toe wedge. We have them running overground at 3.9 meters per second while collecting data from the X-sensor insoles. And the variables of interest were the change in center of pressure position and the propulsion moment. Data was processed using the same techniques as study 1. And the same way we calculated propulsion moment and presented it over 65 to 95% of stance will be presented for the forcing emissions testing. All right, so with the delta COP or the change in the center of pressure position, we have the center of pressure position graph here on the left, over 65 to 95% of stance in the four-shoe conditions. The blue and the purple shoes are the original Vaporfly and the EVA condition, and we can see that the curves look very similar for both of these shoes. The green is the no plate condition, and the orange is the toe wedge condition, which also looks similar but different from the other two, in that they're more anterior in their center of pressure position. And with the toe wedge condition, it is also different from the no plate, where it starts to flatten out at the end of stance, which is what we would expect having seen the results of our flat shoes in the previous study. When we calculate delta COP, which was the difference between the most anterior point and the last point in stance phase, we have the bar graph here for the same four shoe conditions. And we found that we're able to affect the change in the center of pressure position by affecting the features of the Vaporfly. All of the modified conditions showed a smaller change in the center of pressure position, but the only significant difference was in the Vaporfly and the toe wedge condition. Also, it is important to note here that the only comparisons were made with all the modifications compared to the original condition. So there may be significant differences between the EVA and the toe wedge, but for this graph, the only comparisons were with the original. So if this change in center of pressure is an indirect indicator of the teeter-totter moment, based on these initial results, we can make certain expectations for the next results to come. One of those is that having seen a difference in the change in position, we can expect to see a change in the propulsion moment. Based on these results on the right, we can also start to make some expectations on which shoe might show the largest difference. If the toe wedge condition is significantly different from the original, we might expect that that shows the least amount of teeter-totter or propulsion moment in late stance phase. That may not be the case, however. So let's walk through these results. On the left, we have the propulsion moment calculated for all four shoe conditions, over 65 to 95% of stance. And at first glance, we can tell that on average, in the 18 participants, we were able to affect the propulsion moment by modifying the features of the Vaporfly. When we calculate the area under the curve of these individual shoes, we see that there are differences in the different shoe conditions, but the only significant difference is between the original Vaporfly and the no plate condition. So we expected that we would see a difference in the propulsion moment, and we do see that. We expected that the toe wedge condition would show the smallest propulsion moment, but we see something else where the no plate shows that. And even though this may seem weird at first glance, it can be explained by a few facts in how we modify the shoes. So in eliminating the toe spring, you may remember that we use the Pevex foam harvested from the EVA condition, which was the same midsole as the Nike Vaporfly. It's extremely squishy and compliant, and so we expect that when the runners were propelling in late stance phase in this shoe, they were able to compress that foam and still utilize the teeter-totter mechanism to some extent. Not to the full extent as the Vaporfly, but still to some. We also hadn't taken out the carbon fiber plate in that shoe condition, so they still had the stiffness to allow them to compress that foam. So from the second study, we find that propulsion moment was lowest in the no plate condition and that it was largest in the original Vaporfly and EVA conditions, suggesting that the stiffness of the midsole and the geometry of the forefoot may be more important in the Vaporfly in providing the performance benefits. From the two studies, we were able to experimentally support the teeter-totter theory and to come up with a methodology to compare different footwear features. And we also were able to show that this methodology is sensitive to changes in footwear features. However, there were some limitations. First, we assumed a constant muscle moment for a given task. This may not be the case. It may be that a different shoe condition requires a larger or a smaller muscle moment, depending on how the teeter-totter moment contributes to the propulsion. And in the future, studies should measure muscle activation using EMG in order to confirm whether that assumption is good or not. We also were not able to suggest an order of magnitude at this point for the teeter-totter moment estimated relative to the moments at the other joints, for example, the MTP or the ankle joint. And lastly, we were not able to confirm whether the teeter-totter theory is responsible or can explain the performance benefits of the Vaporfly shoe, as we did not measure running economy in these shoes. I'm still 1 year away from hopefully finishing my PhD, and the plan is to answer all of these questions in the next year. So the first thing I will do is compare muscle activity in the 4 shoe conditions that we collected to see whether our assumption of a constant muscle movement holds strongly or not. That data is collected. The data set that I showed today included a lot more data collection. It was 3 hours long, and we collected X sensor pressure insoles, we collected EMG data, the motion capture data, and force plate data. So we have all of the data required to analyze that. Second, I would like to determine an order of magnitude of the teeter-totter moment relative to the MTP and ankle joint moments. And again, we have the data that will be analyzed. Lastly, I would like to determine the effect of the different shoe features on running economy, and to also try and understand whether the teeter-totter moment that we see in the different shoes can explain the running economy benefits seen in the Vaporfly. The experiments for this will be conducted later this year, and I hope to be able to share some exciting results with you before the end of my thesis. I would like to acknowledge everyone that has helped me and supported me throughout this project and made it possible for me to share all of these exciting results with you today.
Okay, who wants to get started with questions?
All right, I will. Sure. The first one, can you explain again? The XAP is just calculated from the rear foot section? Like because you split
This
the,
one?
yeah, you split the, yeah, exactly.
No, this is the entire center of pressure across
the
the
entire-
entire insole.
Okay.
Yes.
And so what causes it to drop down at the end?
The increase that we see in the forces in the rear part of the shoe causes it to move posteriorly. So if you're seeing a more posterior shift in the Vaporfly, for example, there would be a higher force in that rear foot region of the foot in that part.
Okay, thanks. All right. You need to explain something to me. So by and large, this assumption of constant muscle movement, that is the biggest limitation of this entire analogy. So I'm sure you've thought about it. But in my mind, the muscle moment determines the force distribution on the bottom of the foot. It determines the center of pressure location on the bottom of the foot. And so I just want to make sure that all this stuff that you're measuring isn't really just the fact that the muscle movements are changing when you're in these different footwear conditions. So how do you, apart from the EMG that you haven't done yet, or maybe you've analyzed it and you haven't shared it yet, how do you justify that assumption? Because that, to me, that's the biggest assumption.
In my mind, I have two possibilities with that assumption. One, I think it would stay the same in specifically shoes with construction similar to AFTs. That is the assumption that we made. And the second possibility in my mind is that if a shoe with an AFT construction is providing this increased teeter-totter moment, you may even need a smaller force required by the muscles to propel the runner forward. And so that would even support a much larger added teeter-totter moment. That's how I see it.
I just want to make sure it's not a self-fulfilling prophecy.
No.
You could have a lower moment for the force, and because you have the lower ankle moment for the force, the center of pressure is further backwards, and you interpret that as increased reaction force from a teeter-totter effect, as opposed to just the fact that there's less work being done by the muscle. Imagine
Right.
something perfectly rigid and you generate this huge ankle moment. All that force gets transferred to the tip of the toes.
Mhm.
And so I'm just thinking less muscle moment further back. So be really interesting to see the EMG data.
I agree. That is the biggest limitation here, and that's why going from that first study to the second one where we compared all of the shoe features, the first step was to add EMG.
Yeah. And then, I was gonna ask, are any of these conditions where you rip out the plate or you change it to the EVA? I guess to some extent it would be the EVA condition. The EVA condition, would you say that that would be representative of a typical running shoe that people run in, like before the 4% was created? Would that be representative of like a typical running shoe?
No.
No. So what would be the big, I asked just because if you go back
Which one?
to the, where you were showing those teeter-totter there. The EVA shoe basically shows the exact same thing, almost the exact same thing as the VP4 shoe. And so while I think it's effective to look at Vaporfly versus something like an Air Force One, people weren't breaking records because they stopped running in Air Force runs. So I'm just wondering if the EVA, just wondering if other running shoes would illustrate this similar sort of Delta XAP that you call it.
We did it and we had a control shoe, which was a Nike conventional running shoe pre-AFT times, just to see what it looks like. And it was still showing a posterior movement, but not close to what we see in the original Vaporfly.
Okay.
That's why the control shoe chosen in the first paper or the first study, which was sort of a proof of concept of this theory, was a completely flat shoe, which would not allow you to rock over any sort of pivot axis.
Yeah, okay, great, thanks.
So there was one graph he showed that was for it was like the individual profile in the BP4 shoe. And when I was looking at it, it had all the participants, and it was like, it was almost like I know you didn't have a huge sample size, but it was almost, to me, even though sample size notwithstanding, almost like there was like little clusters of people. Like there were 3 or 4 people that were right at the bottom that showed almost no real effect. And then there's a bunch in the middle, and then there's some that are huge.
Yeah. And
that even transpires in your data that when you sort of aggregate it and average it out, what's going on there?
I think with the Vaporflies, there are, well, I don't think it's supported by certain results that we've seen before, but there are responders and non-responders.
Right.
And we've seen up to 10-12% improvements in running economy
Yeah.
for some runners versus some people even showing a detriment.
Yeah.
So I think that's where the responders and non-responders come in. We had these completely different shoe conditions with the Vaporfly and the flat shoe. And so that's the reason that we still see a higher propulsion moment in the Vaporfly. But as soon as we start to compare these shoes that are very similar and only changing in certain features, I think the responder versus non-responder analysis really comes in, which I hope to include in my thesis as well.
And so
Because I might be a runner that benefits more, a little bit more from the plate versus you might benefit more from that 4-foot geometry.
Oh.
Right, and so if that's the case, I would show a larger propulsion moment in that shoe versus the other.
So what do you think determines whether or not the weight, the VP4 is good for somebody?
Honestly, I don't know at this time, but based on what we're seeing here, if it would be ideal if moving forward, we collected running economy measurements for the same data set and went back to see whether their propulsion moment, you know, those subjects that have this huge curve versus those that are flatter on the one that you mentioned, relates somehow to what you see in the running economy improvements for them. And if that's the case, then it would help explain, but if it's not, I'll have to think more about why.
Did you control in the study for rear foot, forefoot runners? Or
Yes, they were all rear foot runners.
they're all rear foot, so probably not technique. So something else.
Well, even in rear foot running, it could be a different landing mechanism that they're using. It could be a different solution specific to that participant. So I don't think by just including rear foot runners, we eliminate that theory. And we should be able to answer that question based on the motion capture data.
To Brent's point, do you think it has anything to do with plantar flexor strength? Like, would a stronger person benefit less from something and a weaker person cap wise benefit more?
Could be, I would think so.
Someone who I should research it. What's a toe spring? Can you describe what are people talking about when they talk about the toe spring?
This upward curvature of the foot part of the shoe.
Just the curvature? So it's got nothing to do with storing and releasing energy or nothing's feeding and like I just think of a spring and I think something compressing and releasing, but
Right, no, from what I understand, it's just this curvature of the shoe.
it's good.
In the forefoot.
So when you did the delta X AP versus the moment, the delta X AP occurs like, it was in like the last 10% of stance, but the moment you took the integral across, 65 to 30% of the stance. Why'd you do that? Because like at the end, the lines get closer and closer, and if you just took the integral at the same position, and that you have the delta X measurement, are you really going to see the same differences?
I think if we were to take the integral in just the part where we see the delta X, I think we'd have a larger correlation. It would only improve the results, is what I think. But the reason for taking all of that 65 to 95% of stance is because the delta XAP in itself is not a functional explanation or a result of what's happening in these shoes. And so the teeter-totter moment, which occurs from 65 to 95% of stance, is the main variable of interest. And the idea and the correlation is to understand whether visually looking at the center of pressure, we can get a first indication of what might happen. But by limiting us to a smaller window in the teeter-totter moment, I think we would lose information. That is more important.
Yeah, I'd agree to disagree, I guess. Simply because like it's not really like versus like that you're comparing here. You're saying that like this delta X change is going to be maybe related to this, but it's not because of this mechanism. It's just, it could be due to anything, at this point. But maybe I'm not thinking about it correctly.
Well, so there is one part of the two variables that is connected or common, and that's the only one, which is the force in the rear part of the shoe, right? That dictates how much the center of pressure moves posteriorly, and the force in the rear part of the foot also dictates how much teeter-totter moment you would generate in the way that it's calculated. So that's a common thing linking the two.
Yeah. Fine by me. We can chat about this later. It's like me taking up more time here. This is unrelated. I'll keep going if no one else has other questions. If you have this bigger moment, shouldn't you see an increased force in the forefoot? Because it's going to act to rotate about the MTP joint, thus applying more force to the forefoot of the shoe?
Maybe, maybe not. I processed all of the data, but yesterday, while practicing my presentation, we also thought about the fact that we should look into what's going on at the forefoot.
Okay.
Because we so far ignored that part. And so it could be that if there's higher forces on the forefoot, I'm not sure yet.
Because that would, I mean, make a lot of sense though, you have more propulsive force. Potentially,
Yeah.
like, right, it's like you are extending the center of pressure in the forefoot and the force is higher. Then you get better propulsion. Then the
Yeah,
second one is,
I
shouldn't
see
there
that.
be a moment about, there should be increased moment about the ankle because of this teeter-totter moment, because it's gonna act to this, it's gonna produce a force that is posterior to the MTP but anterior to the ankle joint. So shouldn't you see a change in ankle dorsiflexion angle?
I would expect to see a change, yes.
But there's no kinematic data yet for that.
There's data, there's no results yet.
Okay.
Yeah.
Okay, going back to the rear foot versus forefoot question, just more of a general question. Has the Vaporfly been shown to actually improve running economy or performance for forefoot runners as compared to the same rear foot and midfoot runners?
I know there's one study that talks about it, they didn't specifically compare it, but they did start to compare it post-hoc to see if there is a difference of prevents. In the treadmill, like the running economy measured over treadmill, I'm pretty sure they didn't find large differences between the rear foots and the forefoot runners, but I'm not 100% sure of that. I would have to go back and double check.
Right, you're saying because in a forefoot runner, you might not actually see that Teeter-Totter effect, would that be correct?
Right.
Yeah.
Not sure. I will go back to you with that. Come back to you with that.
And just another thing on Matt's point around the individual differences. I'm wondering, where is this pivot point in application to someone's MTP? Is it here, behind?
I have the data to be able to quantify that, haven't looked at it yet because I measured physically everyone's metrics. And so one of the measurements was the FTP joint location. And I proposed that as a sub-objective in my PhD proposal where I would speculate that if your MTP joint and the pivot axis of the shoe align, you would have a larger benefit. Because then your innate foot anatomy is also pivoting about the same point as the shoe. Versus someone's being forward or backwards would affect that. I don't expect someone's MTP joint to be very different relative to where the pivot axis is, because in this study, the shoe size was just one shoe size and most people had similar length feet, but it is an interesting point that I hope to look at.
I'm just thinking if I was to wear a size 14, then I'm a size 9 or something like this.
Yeah.
That pivot point's going to be quite low and front, and hence eventually I have to make quite a large moment to get the shoe to rotate.
Right. And that could go back into the responders versus non-responders, that it may be that somebody who's showing less results, their anatomy is not aligning that well with the shoe versus someone else that showed larger.
If you manipulate that by, like, if we're manufacturing these shoes, you could change like the point lines that inside of it.
Potentially, yes. I mean, at higher levels, elite athletes, they do get custom modifications for their shoes or custom made shoes. So I would want to match, but looking at the rest of the data might give us a better understanding of that.
Right?
I ran up and down the hall wearing some Vaporfly 4s the other day. Because Bill had some and they were here. So I ran up to them. And it was my first time trying them on. And one of the things that I observed like the most, that I felt the most, was by far the cushioning. it was, it was like no other shoe I ran ever in my life. And it was all the cushion to me, to my perception. So, you know, I guess you're most familiar with the literature. What does the literature suggest regarding the importance of the cushioning, the heel toe drop of this shoe, and the role that sort of the first part of stance plays in these energetic savings that people get?
Well, from the literature related to the Vaporfly specifically and that foam thickness and material, the Hukamer paper did look at the energy storage and return through material tests, and it was way more than the TPU or the other shoes that they tested. But the question is, does it, that energy stored and returned, does it act at the right time, and whether it is responsible for the improved performance? I've not answered that question.
Yeah, I don't even, not even thinking about the material properties of the shoe itself. It's more the muscle work with the foot interacting with the shoe. There's a lot of subtalar foot motion that takes place during the first 50% of stance. And I don't know how that cushioning would influence that, but I feel like it would influence it in some way. And so I don't know if anyone's looked at that.
Well, the midsole study that Zach did in his PhD was, I think he affected the thickness of the midsole, if I'm not mistaken, and measured running economy and a bunch of other variables. Didn't find a huge difference by changing the midsole thickness. And so based on that,
If I remember Zach's work correctly, he found reduced ankle eversion. Reduced ankle eversion. And correct me. In the lower shoes. In the lower shoe, yes. Decreased ankle eversion. Okay, so it increased with thickness, but then also the energetic cost of running increased with thickness. There's no difference.
But the biomechanical variables indicated that you should be more beneficial at a thicker midsole, but there's no VO2 difference.
Oh, okay.
And it's interesting, you mentioned, so did you only run up and down the stairs, or did you try running straight in the line?
No. Did I say stairs?
Yeah.
I meant hallway.
Okay.
I meant hallway.
I was like,
I don't run up
that's
and downstairs. If I look like
That's an interesting test, absolutely, no one runs. But it's interesting that you mentioned, for you, the biggest thing that you paid attention to was the cushioning. When all of my 15 to 18 participants always said that it was when in late stance phase, they almost felt like they were being pushed enough to fall face forward. So they always noticed the curvature in the toe more than the cushioning. And interestingly, they loved the EVA more than any other shoe condition. They're like, it takes the best parts of every shoe and puts it in one, because you have the stiff plate, you have the toe spring to roll over, but then you don't feel like you're jiggling on this trampoline-like midsole. So I don't know, it would be interesting to see the other results that we find in the future. It might be that we created Vaporfly 5.0 or something.
What was the title of your study? Like when they came in, they see informed consent. What was the title say? To say something about teeter-totters and forefoot curvatures and
the title of
that
this
could
talk.
apply us then towards focusing on the carbon.
Oh, the consent
curvature
form.
rather than like
Oh,
the squishiness of the sheep.
yeah, they're like, where do we sign? But it just said teeter-totter effect, possible explanation of it.
Okay.
They didn't know which feature we want. So
Okay, any last questions? No? Okay. Thank you again.